Hello the students of HS first year. So in my last class I have discussed states of matter, different types of intermolecular forces, that is London forces, Kisom forces and Boyle's law. Now Boyle's law states that V is inversely proportional to pressure at constant temperature. V is inversely proportional to pressure at constant temperature. Next is our Charles' law. So Charles' law is that this law states that when the pressure remains constant, the volume of a given mass of a gas increases or decreases by 1/273th of its volume at 0 degree centigrade for every 1 degree rise or fall in temperature. So our Charles' law is that when the pressure remains constant, volume of a given mass of a gas increases or decreases. So if we write Vt is equal to V naught into 1 plus T degree centigrade by 273, where Vt is the volume at T degree centigrade and V naught is the volume at 0 degree centigrade. So this is our Charles' law. In another way, we can also explain Charles' law that at constant pressure, volume of a given mass of a gas is directly proportional to temperature. So from this, mathematically, we can write V is directly proportional to T. So V1 is also directly proportional to T. So from this, we can write V1 by V2 is equal to our T1 by T2. So in this way, we can also write V1 by V2 is equal to T1 by T2 is equal to constant. So this is our Charles' law. Now from Charles' law, we can also define one important term. The term is absolute zero temperature. That is, from Charles' law, we can write Vt is equal to V naught into 1 plus T degree centigrade divided by 273. Now, if the temperature is minus 273 degrees centigrade, so putting the value of this T in this equation, we get our Vt is equal to, that is, V naught into 1 plus minus 273. Here we put minus 273 divided by 273 is equal to 0. So at 0 degree centigrade, at minus 273 degree, the volume of a gas becomes 0. So this is known as our absolute zero temperature. So in this temperature, gases ceases to exist. Gases ceases to exist. So it is termed as absolute zero temperature. And it is an interesting point to note that absolute zero temperature has no physical significance. So this point should be noted that absolute zero temperature has no physical significance because all the gases get liquefied or solidified before minus 273 degree centigrade. So this is our Charles' law. Then another law is known as Galusha's law. And this is the pressure-temperature relationship. Galusha's law of gaseous volume, we have found this in our previous unit. But here the Galusha's law of gaseous volume is pressure-temperature relationship. So P is directly proportional to T. Here also a constant volume pressure of a given mass of a gas is directly proportional to temperature. So P is directly proportional to temperature. So we can also write P1 is directly proportional to T1. So from this we can write our P by T is equal to constant. Similarly, P1 by T1 is also constant. So from this we can write P by T is equal to P1 by T1 is equal to constant. So if we plot a graph in between pressure and temperature at constant volume, we get different types of straight lines. That is V1, V2, V3, and these are at constant volume. So these are isopores. These graphs are called isopores. Next is our Avogadro's law. And Avogadro's law, all of us know that at constant temperature and pressure, equal volume of all gases under the same condition of temperature and pressure contain the same number of molecules. That is this n, small n. So our V is directly proportional to n. Similarly, our V is equal to some constant into n. So this is our these are our Boyle's law, Charles' law, Galusha's law, and our Avogadro's law. Next is our Dalton's law of partial pressure. This law states that at constant temperature, if two or more gases does not react with each other and they are enclosed in a space, the total pressure exerted by the gas molecule is equal to the sum total of the partial pressures. That is our P is equal to P1 plus P2 plus P3 dot 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 dot. So this is our Dalton's law. Again, we can also write that this P1 this P1 we can write P1 V1 by V1 plus V2 plus this is our P2, so we can write P2 V2 divided by V1 plus V2. So this is our Dalton's law of partial pressure. And again, the partial pressures of any constituent of a mixture of gases can be obtained by multiplying the total pressure of the gas mixture by the mole fraction. So we can write also PA. If the component is A, that is the partial pressure of the individual gas A. So PA is equal to mole fraction of the A into total pressure. So Dalton's law of partial pressure can be stated in two ways. One is the total pressure exerted by the gas molecule is equal to the sum total of the partial pressures. That is P is equal to P1 plus P2. Then in case of P1, we can write P1 V1 by V1 plus V2. And in case of P2, we can write P2 V2 divided by V1 plus V2. In another way, the partial pressure of a individual gas molecule can be expressed by the mole fraction of that component into total pressure. So this is our Dalton's law of partial pressure. Next is our Graham's law of diffusion. This law states that under similar condition of temperature and pressure, the rate of diffusion of gases are inversely proportional to the square root of their densities. That is, R is inversely proportional to the square root of density. So Graham's law states that under similar conditions of temperature and pressure, the rate of diffusion of a gas molecule is inversely proportional to the square root of the density. That is, R is inversely proportional to density. Similarly, we can write R1 is proportional to D1, R2 is proportional to this. So from this, we can write our R1 by R2 is equal to root over D2 by D1. Root over D2 by D1. That is, D2 and D1 are the densities of the two gas molecules. Now, replacing densities, we can also write R1 by R2 is equal to root over small d2. That is, similarly, R1 by R2 is equal to root over d2 by root over d1. So, in this way, we can express this. Also, we can express the rate of diffusion in terms of molar mass. That is root over m2 by m1. So, the rate of diffusion can be expressed in different ways. One is R1 by R2 is equal to root over d2 by d1, or R1 by R2 is equal to root over small d2 by d1, or R1 by R2 is equal to root over m2 by M1. So these are the different types of gas laws. The next term is our ideal gas equation. Now, in solving various problems, we can use different values of capital R. Now, what is this R? This R is our molar gas constant. Molar gas constant. Now, from Boyle's law, we know that V is inversely proportional to P. This is our Boyle's law. Second is our Charles' law. So from Charles' law, we can write that our V is directly proportional to T. So this is our Boyle's law. This is our Charles' law. And Avogadro's law is V is directly proportional to N. So this is our Boyle's law. At constant temperature, V is inversely proportional to P, and Charles' law is at constant pressure, V is directly proportional to T, and Avogadro's law is at constant temperature and pressure, V is directly proportional to N. Now, combining these three, we can write V is proportional to NT divided by P. NT divided by P. Now, PV is, that is, from this we can write PV is proportional to NT. So we can write PV is equal to nRT. So PV is equal to nRT. So this R is our ideal gas constant or universal gas constant, and we can solve different types of problems by using different values of R. And one value of R is PV by RT. So if we put the value of pressure, that is in this way, that is our R is equal to PV by NT. Now if we put in place of pressure 1 atmosphere, and in case of volume 22.4 liter, and similarly this N is 1 mole and this T is 273 K. So in this way we can calculate that the value will be 0.0821 atmosphere liter atmosphere temperature inverse and mole inverse. Yes. So if we put in place of pressure 1 atmosphere, in case of volume 22.4 liter, in case of N 1 mole, and in case of temperature 273. So we will get this value. In another way also, another value is I think 8.314 Newton meter per mole per K. So these two values of R are very much important, and we can also solve different type of problems by using the value of R. So now I will give one problem for you because in HS first year and second year problems are very much important, and in the class it is not possible to do all the problems, but I will try a little bit. Yes. So one question is, suppose the mass of diatomic gas, the mass of diatomic gas at 0 degrees centigrade and 2 atmosphere pressure is 1 gram. Calculate the molar mass. So the question is the mass of diatomic gas at 0 degrees centigrade and 2 atmosphere pressure is 1 gram. Remember, calculate the molar mass. First of all, You read once or twice the question and then you write the equation which is used for this problem. So the equation is our PV is equal to nRT. Our equation is this, and here given our P is equal to 2 atmosphere, is not it? P is equal to 2 atmosphere, V is equal to V. The atomic gas 0 degree centigrade. So our V is what? P is equal to 1 atmosphere. Our R is equal to 0.082 liter atmosphere per Kelvin per mole. And our V is equal to 350 ml. That is 0.35 liter. So by using this, we can calculate M, and the value of M is 32.09 gram per mole. So in this class, we have discussed first Charles' law, then what is absolute zero temperature, then what is the physical significance of absolute zero, then Galusha's law, this is the law between pressure and temperature, then Avogadro's law, then ideal gas equation, and then one problem. So it is not possible for me to do all the problems here, and you practice the problems at your home. So this much for today. Thank you very much.